Hey everyone, welcome into this lecture on the inverse function theorem. I'd like to start this lecture by stating the theorem as it's posed in the text, and then I will draw some pictures and we'll do an example. The theorem says this. It says if f is a one-to-one function, I'm abbreviating one-to-one here, but if it's a one-to-one function with an inverse function, so with inverse function f inverse on an interval, so on an interval from a to b, I'm adding a little bit to this theorem that's not in the book, but it's pretty much the same as what's in the book. And let's suppose that f prime of c is not equal to 0, very important, not equal to 0 for c between these endpoints, a and b. So less than or equal to c, a less than or equal to c, less than or equal to b. And finally, if f of c is equal to d, then here's the result, and this is the main thing, okay? The result says that the derivative of the inverse function is defined at d, and that it's related to the derivative of f, the original function, at c. So here's how we read it. F inverse prime at d is equal to 1 over the derivative of f at c. All right, and so there's the inverse function theorem. So a couple of things going on here. First of all, we need to know, what does it mean for a function to be one-to-one? How is it related to its inverse function? So this is a review lecture, so hopefully these words at least look familiar, and you guys can go back and look up the stuff that you really don't remember. But I'm going to sketch a little picture here, because the relationship between the derivative of the inverse function and the derivative of the function itself is very geometric, and that should not be a surprise, because all of calculus is in some sense applied or analytic geometry. So let's try to sketch this, all right? I'm going to sketch, and I'm just going to sketch a very special case of this, all right? So here's our xy axes. In red here, I'm going to sketch a curve like this, and we're going to assume that that derivative is at the endpoint is not 0. All right, so it might be close to 0, but not 0. And we'll say that this is our interval from a to b. This is our curve y equals f of x. Now, this curve is one-to-one. The curve, so the function represented by this curve is one-to-one. And the way that we can tell that is we just apply what's called the horizontal line test. I'm sure you remember that to be a function, your curve, to be the graph of a function, your curve must pass what's called the vertical line test, right? And that says that for every vertical line that you draw, the curve should cross exactly once, right? It should cross exactly once if you draw the vertical lines within the domain. So this does pass that. That makes it a function, but it also passes the horizontal line test. And the horizontal line test tells you that the function is one-to-one. The corresponding function is one-to-one. And if it's one-to-one, then it has an inverse, okay? How do we find the inverse? Well, this is a completely geometric interpretation, but the inverse function of f exchanges the roles of x and y. All right, it exchanges the roles of x and y. And so the way that you draw this geometrically, you suppose you draw the line here, y equals x, and you suppose that you could reflect your curve over this, right, so that these are equidistant, so that it's perpendicular. So if you were to connect all these points, right, that they're perpendicular to this line y equals x, and then the curve just kind of does something like this. All right, and so this graph right here, and you know, maybe it's not perfect, but the idea here is that if you were to connect point to point with perpendicular lines, that these would be equidistant from the blue line, the light blue line. And again, maybe my picture is not perfect, but that's the idea. All right, so there's the graph of y inverse of x. Now, what is this doing in reality? Well, it's just treating the curve, this curve portion, instead of treating that curve portion like a function in the vertical direction like we're used to, right, where the x's are the inputs and the y's are the outputs, it's treating this, like here, let's call this a star, and let's call this one over here, say b star. It's treating this red graph like a function where the y's are the inputs and the red points are, and then the x's are the outputs, right? And so the idea here is that if you were to flip everything around, the red would become the blue would become the red, vice versa. Okay, and so that's the relationship between a function's graph and the graph of its inverse function, if it has one, All right, even if this, and by the way, it always has an inverse relation, because you can always switch the axes, right? But the question is it an inverse function? Is it a function? And because our red curve obeys the horizontal line test, our blue curve must obey the vertical line test, because when we do the reflection, horizontal becomes vertical. Okay, so there's just a reminder of what it means to be inverse function and how the graphs are related. Now here's what the theorem says, though. The theorem says that if your function that corresponds to the red curve is differentiable at this point C, right, which is in between A and B, and the derivative is not 0. So that means that the tangent line is not horizontal, right? Then the slope of this tangent line, of course, is f prime of C. That's what it means to be a derivative. It's an instantaneous rate of change, the slope of the tangent line at that point C. But what this also tells us then is that this point over here, the corresponding point on our inverse function, this one, which by the way, its input is d down here. How do we know that? Well, that's the d, that's the height of this point over here. All right, so those two are, you know, you got to use your imagination with my picture here. But the idea is that those two are the same value. And the slope of the tangent line to this one is the reciprocal. Well, how can we see that geometrically? Well, this has been reflected over the line y equals x. So its slope, right, its slope is f inverse prime at d, just by definition. But the theorem says that that's the reflection. So it's the reciprocal because we reflect it over this line. It's the reflection of the slope of the corresponding point on the curve itself. Now, it's very important here, and then this is why it's good to draw the picture. It's very important to notice, right, that the D and the C are not the same point, right? The D and the C are not the same point. The D is the point that comes from the inverse function, right? It's the height of the output of the point here, C. So if we were going to write this, by the way, if we were going to write this in terms of this, when this is D, this must be C up here, right? That's the way it's got to work. So if we could write this relationship slightly differently, we could write, all right, f inverse prime at D, all right, the derivative of the inverse function at D is equal to 1 over f prime at f inverse of D. But that's exactly C. So that's exactly the point C. This is equal to C by our picture here. So it's the point where this comes from, right? All right, so there's just a review of the inverse function theorem. It's a very important theorem. Let's now take a moment to look at an example. And we're going to compute this one two ways. So first of all, here's an example. Here's a function. This function, I'm just, you know, winging it here. But let's say we have the function y equals x plus 1 over x minus 2. All right, and we want to try to understand this function and compute its inverse function, you know, look at the derivative at some point. So first of all, let's sketch the graph of this thing. How are we going to sketch the graph? Well, one way to sketch the graph is to rewrite this in a slightly different form. All right, so if we were to just do a little adjusting on the top, we could write this as x minus 2 plus 3 in the numerator. And look at, if you add negative 2 plus 3, you get 1. So I haven't changed anything, right? But what I've done is I've gotten this so that now I can break this up. Right here. And I can write this as x minus 2 over x minus 2 plus 3 over x minus 2. And at this point, we have to be very careful because x minus 2, this ratio, right, should be 1. But it's 1 everywhere except when x equals 2. Because if x equals 2, this is 0 over 0 is undefined, right? X equals 2 is also bad here, though. So actually, I can write this as just 1 plus 3 over x minus 2 and not lose any information about the domain of this function because it's still visible, right? It's still visible in this x minus 2 term down here. But this one allows us to sketch the graph very easily, right? So this one has a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 2, and otherwise it looks like a hyperbola. So just breaking up your function can help you sketch its graph very easily. So we said horizontal asymptote is at y equals 1. That's because this will never be 0, right? We approach this as x gets very large, I guess, we'll approach this asymptote. But otherwise, you know, we'll be far away from it. And then the other one is when x equals 2, and obviously that's because you can't divide by 0, right? All right, and so then our curve, when x is positive, or when x is bigger than 2, I should say, this term is positive, and so we end up with a curve that looks like this. And it becomes negative on this side. Should be pretty symmetric. It should not get that close to the asymptote right there. So there we go. So there's our curve, y equals x plus 1 divided by x minus 2. All right, let's now take a moment to find the inverse function of this curve. So this, by the way, the domain, let's call this f, right? So the domain of f is equal to, it's the set of all points except x equals 2, right? So it's the set of all x not equal to 2. All right, it's equal to, it's got every other point is in the domain though. And this is for our f of x equal to x plus 1 over x minus 2. All right, well, let's do a couple things. First of all, let's find f of 3. F of 3, I'm going to use this formula now, is going to be 1 plus 3 over 3 minus 2. 1 plus 3 over 1, so that's 4, right? Now let's find f prime at 3 as well. So f prime at 3 is going to be what? F prime of 3 is going to be 0. This part's gone. And then this is just a chain rule, right? This is just a chain rule. So this derivative is going to be 0 plus the derivative of 1 over u is negative 1 over u squared. So this is actually going to be negative 3 over x minus 2 squared. This is the derivative. I wrote a 3 in here. That's our goal. I want to plug in a 3. But first, here's our derivative of f of x. So, yeah, that's good. Leave it like that. And now I want to plug in 3. So f prime at 3 is going to be equal to negative 3 over 3 minus 2 quantity squared. Well, that's negative 3 over 1, so it's negative 3, right? Our inverse function theorem says that, number one, our function has an inverse at this point. 3 is over here. It's in our domain, right? So there's our point where we're looking, and the slope of this should be negative 3. The height should be 4, right? The inverse function theorem says if we just look at everything sideways, right, then this point right here should correspond to a point on the inverse function curve, just going from left to right instead of down to up, right? And the slope of this line should be the reciprocal of the slope of, itself. It's the same line when you look at it this way, right? The tangent line is the same line, but the rise over run, we've changed the roles of the x and the y. So the rise is happening this way, and the run is happening this way. So let's compute, right? We want to know then the derivative of the inverse function at the inverse function's input has to be 4, right? So f prime at 4. By the inverse function theorem, this is 1 over f prime at 3. Maybe I should color code this better. 3 comes from here, right? And according to the rule, then, this is just 1 over negative 3, or negative 1/3. All right, but let's compute this and make sure that it's actually right. So to actually compute it, we have to find a formula for the inverse function, and then we have to take its derivative and plug in 4, right? X equals 4 in that case. So this is what we expect. Let's make sure we actually get it. So remember, our function itself was y equals x plus 1 over x minus 2. We want to swap the roles of x and y, right, to find the inverse function. And so what you do is you just swap these out, right? You write this as x equals y plus 1 over y minus 2, and then you try to solve for y. This is, hopefully you remember doing this, right? This is how you find the formula for the inverse function when you're given the function to begin with. So a little cross multiplying gives us x times y minus 2 equals y plus 1, and then some rearranging says we have x times y minus y equals 1 plus 2x. So, distribute the x and then rearrange. And then we can factor out and write this as y times x minus 1 equals 1 plus 2x. And finally here we get y equals 1 plus 2x over x minus 1. All right, now first of all, we should ask some questions. Does this make sense, right? What's the domain? Now, I guess first of all, we've got y equals something up here. We've got y equals something down here, and they're different, right? Those two y's are different. So what we should now do is write, this is the formula for our inverse function, right? So we should give it the name f inverse of x equals 1 over 2x over x minus 1. 1 plus 2x, over x minus 1. Now remember, our whole point of view here geometrically is that we've just turned everything on its side, right? And so the domain becomes the y-axis, and of course y equals 1, this what was our horizontal asymptote for the original curve becomes a vertical asymptote for our new curve, and so that point can't be in the domain, right? But when we've switched everything's roll down here, that means x equals 1 can't be in the domain, and we see that that's exactly right. And then the other thing we see is that as x gets very large, the ratio of the leading coefficients is 2 over 1, right? And we go back up and look at that. So that's going to be our horizontal asymptote for our inverse function. It was the vertical asymptote for our original curve. It was at x equals 2. Now it's at y equals 2, right? By switching the roles of x and y. All right, so this is perfectly fine. Now what we want to do is take the derivative of this. So f inverse, let's take the derivative by applying the quotient rule. All right, so f inverse prime is going to be the derivative of 1 plus 2x over x minus 1 prime. All right, and we know quotient rule says bottom times the derivative of the top. Derivative of the top is 2 minus the top times the derivative of the bottom, that's 1, all divided by the bottom squared. And then we just have to very carefully simplify the top. I mean, we're just going to plug in one value, so we don't really have to simplify, but I want to. So this is going to be 2x minus 2 minus 1 minus 2x. Distribute the minus all over x minus 1 quantity squared. And at this point, look at, we've got 2x minus 2x. All right. And we see we get negative 3, right? Negative 2 minus 1 over x minus 1 quantity squared. And remember, our goal was to try to compute f inverse prime at 4, right? The input that we cared about up here was 4. And we've got our formula. We just have to plug in. So this becomes negative 3 over 4 minus 1 quantity squared. That's negative 3 over 3 times 3. 3 squared is 3 times 3. Cancel, cancel. Look what we get. Negative 1/3. Negative 1/3. Negative 1/3. It's exactly the same. Expected and then obtained, right? So what's the usefulness of the inverse function theorem? Number one, it tells us a whole lot about the geometry of what's happening. Number two, it tells us if we already know the derivative of our function and we know where the point came from, right? So if we know c, given d, if we know c, remember this is the relationship here, right? So given d, if we can find or if we know c, then we automatically know the derivative. And this is not a proof, but we've shown by calculation that it's, at least in this example, it's going to give us the right answer. It turns out it always will give us the right answer. So this is our inverse function theorem.